And I'll just start right into it here. Good evening and welcome to our MOAS virtual talk tonight. My name is Seth Mayo. I'm the curator of astronomy at the Lowell Planetarium, Lowell and Nancy Lohman Family Planetarium, rather, at the Museum of Arts and Sciences. And glad to have you all here. This is a great event. And today, I want to wish everyone a happy International Day of Women and Girls in Science. This is a very, very important holiday for us to celebrate that many people don't know even exists. And it's a day where we can celebrate the inclusiveness and diversity in science by the amazing women and girls that are a part of it, and hopefully will be so in the future. And so I think there's something to that, and something that we should definitely celebrate. So this day was first recognized in 2015 by a resolution from the United Nations General Assembly. We celebrated this for the first time at MOAS last year, and we're very happy we can continue this new tradition. We'll continue it this year in a safe virtual environment, as we see here. Of course, this is something we're all getting used to, kind of a new normal, as we kind of hear all the time. So it's nice to be able to offer this in some way. And we are so pleased to have with us tonight to kind of kick things off, Dr. Addy Dove here to kick off the celebration. She will be speaking tonight on the topic of flying laboratories, exploring dusty planetary surfaces from the ground, the sky, and space. Very cool topic that she's going to discuss. She is a rock star in the science community, and it's always exciting to see what she's working on. So we are so happy to have her, and we've been trying to get her to talk here for some time with us. So it's great to have her for this wonderful event. So before we get started, just a few housekeeping bits just to kind of lay the groundwork for our lecture tonight. Our speaker will present first, of course. We'll get things going in just a moment here. And then we'll have a little time afterwards for any kind of Q&A if there's any questions out there. And while Dr. Dove is presenting, you can post your questions in the Q&A dialog box. And if you have any technical issues, you can post those in the chat box as well. And I'll try to get to those as quickly as I can to help you out. We'll read through your questions at the end of the presentation, and then we'll try to get to as many as we can. So just bear with us with that. And you may also raise your digital hand. There is a digital hand feature. If you want to ask your question through your microphone, if you want to do that. You don't have to do that, but you can. And there is a button to raise your digital hand, and I can allow you to speak for a moment. So let me formally introduce our speaker tonight to get things underway. Dr. Addy Dove is a planetary scientist and assistant professor in the Department of Physics at the University of Central Florida. She received her Bachelor of Science in Physics from the University of Missouri in 2006 and her PhD in Astrophysical and Planetary Science from the University of Colorado Boulder in 2012, focused on planetary surfaces, dust grain, and plasma interactions. Her main research interests are in dust charging and dynamics on planetary surfaces, planet formation and plasma interactions with planetary and spacecraft surfaces. She's particularly interested in these topics because understanding these phenomena is key to successful planetary exploration and will be increasingly important when we are exploring the moon and asteroids. She explores these processes through experiments in the lab and on research flights with parabolic aircraft, suborbital vehicles, the International Space Station, and Cubesats, all really cool things, obviously. She enjoys teaching both in the classroom and outside the classroom through a variety of outreach events like us. So yay, she's here. And is a co-host of the fun astronomy podcast, Walk About the Galaxy, which, by the way, is a wonderful podcast. Please definitely tune into that. They have some great episodes on there about all sorts of cool stuff. So check it out. All right, so without further ado, I'm going to hand it over to Dr. Addy Dove, and thank you very much for all being here tonight. I'll give it to you.
Thank you. All right, let me start this up. Hi, everybody. It's good to be with you tonight. Thanks for that great introduction and the podcast plug. It's always good to get that plug in there. We do talk about a wide variety of topics on Walkabout, and so it's a fun adventure of space news and trivia and current events in astronomy and planetary science. Today I'm going to be a slightly more focused and talk to you about some of my research and the different laboratory environments that I use to do my research. And so it's a lot of that is in the title. So we use different laboratory environments to explore dusty planetary surfaces, and I'll explain a little bit of why those are interesting here in a minute. With things like suborbital vehicles and just even experiments in the lab. So to get started, I wanted to mention that I am at the University of Central Florida and work in a lab that's part of the Center for Microgravity Research. And we also have what's called the Center for Lunar and Asteroid Surface Science at UCF, which is a big NASA-funded institute that is really studying a lot of different processes on planetary surfaces. So a lot of the work here is supported through those different ventures. And I'm really happy to be speaking with you all today, and I'm really excited to see the rest of the speakers this weekend. And I think that a celebration of women and girls in science is really important. And I hope to see future generations continue this tradition. So I just wanted to throw up a few pictures to start, which is a little bit of my background in research and exploration. So I have had a variety of different types of research that I've actually explored over the years. I tend to be interested in a lot of different things and find different ways to explore that. One example of that is that I did a summer research project in Hawaii, and it had nothing to do with lava, but we got to take a field trip and explore the active volcanoes in Hawaii in undergrad. In grad school, I was in Colorado, and so we would do, even though it was not research related, we did a lot of activities that were involved snow. So this is a fun picture. There's a fun picture of me on here doing some science experiments, I'm sure, and testing the hardness of snow or something like that. And more recently here at the University of Central Florida, I've been doing a wide variety of research projects that involve different flight projects, including on Parabolic airplane, which is the airplane that does what are called parabolas in the air. It's sometimes called the vomit comet, but you can do weightlessness in the air. And I put these up here just to show a little bit about my history, and it sort of represents a lot of different aspects of what's interested me and what's sort of kept me in science, is that I think it's just a really fun adventure. And one of the great things about being a scientist and being a researcher is that you get to explore a lot of different environments, you get to travel, you get to meet really fascinating people. And so there are lots of different aspects about my job as a teacher and a researcher that are outside of the classroom and that are really awesome experiences. So let's dive in and talk a little bit about my research. And I'm going to give a little bit of background before talking about the various platforms that we use, those flying laboratories. And the first thing is that I'm going to introduce a term that I'm going to use a lot, so it's an important term to introduce, and that is regolith. And that is basically just a fancy word for the dust and the dirt that's on planetary surfaces like the moon and asteroids. So regolith just means broken up bits of rock, and it can, it's really basically the thing that covers all of these surfaces in space that we're exploring. And a lot of times I'll say dust and I'll say regolith, and I sort of use them interchangeably. Dust is usually the finest parts, but sometimes I'm a little loose with those terms. And so the pictures here show you what some of the dust on the lunar surface specifically looks like. And you can see the classic sort of boot print picture there in the center. We have had both human and robotic interactions with planetary surfaces, with the moon, with asteroids, that are really helping us understand these places. And a lot of my research is to try to make that exploration better and understand what's going to happen and what is happening when we're there. It's not just on the lunar surface, it's also on places like asteroids. And so this slide sort of shows you some of the variety of scales of the features we can see. So you can see on the left, there's a picture of an asteroid called Itokawa, which is a sort of funny, weird potato-shaped asteroid. That's pretty big as asteroids go. Well, I don't know, it's pretty small, it's pretty big. They're all small rocks. but it has weird smooth areas and some bouldery areas on there that you can see. And as you zoom in, you can see that even the areas that look kind of smooth are actually pretty rough and bouldery. And we saw this a lot more when we have gone more recently to the asteroids Bennu and Ryugu. And so these are asteroids that spacecraft have been exploring more recently. And so they have lots of different textures and different rocky buildup on the surface. And so the surface processes that we see and we want to understand are important because they tell us about the history of planetary bodies. So they tell us how that regolith got there, why the rocks are the size and shape they are, why they're distributed the way they are, tell us about the history of these planets and planetary bodies. And they also can tell us a little bit about what's going on inside. And it's going to be really important as we try to land things there or explore these different surfaces to understand what they're really like. So that's why we do this research, to understand regolith and dust. And these surfaces are built up over time. So you can imagine if you sort of start with rocks early in the history of the solar system, they come together. Sometimes you just have loose clumping of rocks. So some asteroids are what are called rubble piles. So they're just sort of loose clumping of rocks. Some are like the moon, or a big solid body with just sort of dust on the surface. And this is produced, the dust on the surface and the modified surfaces of the asteroids are produced by things like impacts. So other things hitting those surfaces. Things like landslides. So you can have landslides on these bodies. And then some more detailed things like what's called electrostatic motion. So this is actually just grains sort of hopping around due to having a charge on their surface, so more electrons and ions. And then also sometimes just heating and cooling a bunch can make things crack and it can break pieces off. So you get all sorts of processes happening on these surfaces that are very different actually a lot of times than what we see here on Earth, because on Earth we have the atmosphere, we have weather, and it really is different than what we see on these bodies. So you can study a lot more sort of basic physics and basic processes on these surfaces. And I can't talk about these surfaces these days without mentioning Hayabusa Ii and Osiris-Rex, which are both spacecraft missions that have recently been exploring asteroids. Hayabusa Ii was a Japanese mission and Osiris-Rex is a US mission. Hayabusa Ii went to an asteroid called Ryugu, so you can see that on the left. And it actually touched down on the surface and got a sample and brought it back. And that sample was returned to Earth in December. So there's now people studying samples of this asteroid. And then Osiris-Rex more recently got to Bennu, and it recently took a sample and it will be coming back in a couple of years. It takes a little while to get back because it's kind of far away in space. So it's going to take a little bit to get back to us, but then we'll have additional samples of a different asteroid to study, which will be super exciting. And these missions, like I said, took samples from the surfaces of these asteroids, which is a huge feat. We only have samples, direct samples from a few places in the solar system, mostly the moon. We have some samples from asteroids and maybe Mars from broken off bits that fly through space and land here as meteorites, but otherwise it's really hard to get samples. So these missions were really exciting. And they had amazing video, of course. So we have some video of the Osiris-Rex sampler touching down on asteroid Bennu. And so this is as it was approaching and just before it touched down. You can see this there's a sample head on the end of the arm in this picture, and it's sort of zooming down in and getting close to the surface. And you can see again here that these surfaces have these boulders and rocks that are all different shapes and sizes. Similarly, we have some video from Hayabusa Ii of its touchdown, and this is one of the actual touchdown videos, and you can see it sort of goes in, gets a little bit, and it actually blows a little bit of air down too, and then it makes stuff go everywhere. So one of the really important things about these asteroids and even the moon is that they have very low gravity. So here on Earth, we're used to what we call 1G or 1 gravity level, basically. And that's sort of the thing that drives our everyday lives, right? Walking around, all of that is because, and we're used to that, is in 1G. On asteroids, it's actually very low gravity. So things that we're used to, like dropping something or touching something and it doesn't really move. If you poke something really gently even on one of these asteroids, it might cause material to fly everywhere. So we see this sort of giant mess of stuff going everywhere from this impact on the surface, but this actually wasn't touching down that fast. It wasn't going miles per second or anything like that. It was going relatively slowly, but because everything is so fragile and so loosely held together on the surface, it sort of is ejected up and goes everywhere. And then once it's ejected off the surface, because the gravity is so low, it can sort of keep flying out into space. So you have really interesting processes happening on these surfaces. So the importance of those things then is that you have space, you have dust and regolith on planetary surfaces, and you have low gravity. So a lot of my research is trying to understand how things behave in these low gravity space environments. And so that usually means things like having a vacuum chamber. So you want to get rid of the effects of air and atmosphere on things. That's both because air, especially in Florida, has a lot of humidity in it and a lot of water and moisture, and that can really change the way things behave. But also because as things are moving through the air, it causes drag on the particles, so it can change their speeds and their motions and their paths that they're going on. And we don't want that. We want to understand sort of how they naturally move. And so that's the vacuum side of things that represents more of the space environment. And then there's the microgravity or low gravity side of things, which turns out is sort of hard to do when you live on a big planet like Earth. And everything else, like I said, happens in 1G. So we do some experiments in 1G to just sort of look at the basic physical processes. So things I mentioned earlier, so some important things that shape these surfaces or impacts. Those are things that shape asteroid surfaces, but as you just saw from the Hayabusa video, it's also as we interact with planetary surfaces, whether it's on asteroids, whether it's an astronaut walking around on the surface of the moon, you'll have impacts on the surface. And so we need to understand how the materials are going to respond and what's going to happen to them as you're moving around. So we do experiments sometimes in Earth gravity just to really understand what's happening. And there's some pictures here of one of our nice vacuum bell jars in our lab. So this is a big giant experiment chamber that we're able to put dirt and different impactors and things like that in and do our experiments. There's a little sort of schematic of what might go inside of that underneath the picture. And then the main picture in the center is an example of where we had a bunch of beads. In this case, they were red plastic beads just to sort of test out the experiment in a cup in the center of the chamber. And then we impact a marble into that cup and we take video from above. And as you can see on the left from the side, to look at what the ejecta or what the material that flies out looks like and what its speeds are and how much energy it's moving with, because that tells us how this might behave on the Earth, but also on other places. And so a really important thing for this is understanding sort of the energy, but also just sort of what these interactions look like. So we do a lot with video data in these experiments. And then a lot of things like particle tracking, where we see on the left, our laser sort of illuminates particles and you can see how they're moving along and we can track those and look at their trajectories and make predictions for the moon or asteroids. So that's in 1G. You can see one of the things you'll notice here in the picture on the left is that the trajectories sort of make parabolas. So they go in arcs. And that's because they're starting to go up, but then their speeds aren't high enough and gravity pulls them back down, right? That happens to almost everything here on Earth. You throw something up, it comes back down. But in really low gravity environments, you send something up, it basically keeps going. And so we have to get to those microgravity environments to see how that works. So we do that in different ways. The first way is what's called a drop tower. So this is just an apparatus, a big setup in our lab that is basically a big thing that lets us pick up an experiment to the ceiling and then drop it to the floor in a safe way, I promise. And this gives us in our lab a little less than a second of free fall time, which doesn't sound like much. But you can actually do a lot of good science in a second if you have really high speed data, so high camera rates, right? So you can, like on your iPhone, you can do the really high camera rates. We can do that with a lot of different cameras on our drop tower. And the way to think about this is that if you've ever been in an elevator where it sort of drops suddenly, or if you're in Florida, right? So maybe you've been to like the Tower of Terror or somewhere like that. You drop suddenly, you sort of float up off your seat a little bit, maybe your stomach comes up a little bit. That's what's called free fall. The astronauts on the space station are always in free fall as the space station is orbiting, it's sort of falling around the Earth, and that's where you get that weightless feeling. And it's just because you're moving at the same speed as things around you, and so it looks like and sort of feels like you're weightless or in microgravity. So we create that little environment in a little vacuum chamber in a little experiment in our lab. And these experiments are cool because we have students at the university build them and run the experiments and test them. And they give us a chance to try out a lot of different types of experiments, but also get some really cool data. So we've done a lot of these impact experiments in these chambers, but we've also done a lot of plume experiments recently, which are related to landing on planetary surfaces. So here's a couple of sort of still shots of that ejecta I was talking about. So you can see from the top down on the right and on side camera on the left, some different images of stuff being shot up after this was a plume impact in low gravity. I also have some videos then of these same effects, and this is to show you the contrast between what happens in 1G on the left and microgravity or low gravity on the right. And so this is the same setup, and it's the same sort of burst of air we're putting into the regolith, into the dirt on the surface here. But on the left, you can see you barely see anything happening. If you look closely, you can see some little, but you don't really see much else. But on the right, in microgravity, you see all this material fly up, really big chunks fly up. And that's because when you're in low gravity, it's easier to move these things. It's easier to make them lift up and separate because gravity isn't holding them down to the surface. So you can have much more dramatic effects in microgravity than you'd expect from your 1G tests. And here's another example of that, where we sort of don't see anything on the left. There may be some stuff flying around, but then this really dramatic experiment on the right. So here the air pulse we did was longer, and you can see it makes quite a mess in our vacuum chambers. One thing about these experiments is all of our experiments have a lot of dust and dirt, and they take a lot of cleanup time. So the next step then from drop tower, from short, less than 1 second experiments, is things like parabolic flights. So I mentioned earlier, we do a bunch of experiments on these reduced gravity flights. And these you have a little bit less than 30 seconds usually to do your science. And they can do, the cool thing about these is you could do microgravity, but you can also do lunar or Martian parabolas where your gravity levels are similar to the moon or Mars. And so it allows you to sort of test different ranges, which is really cool. And a lot of people that do experiments on parabolic flights are testing all sorts of things. So sometimes they're studying human factors like pressure on the eyes or response times and things like that. Sometimes they're studying things like combustion or liquids. But a lot of what we do is these tests to understand grains and particles on surfaces. So the picture sort of in the middle is an older experiment that we had where it's floating in the cabin, and that's so there's none of these external forces on it. Sometimes we have things attached to the airplane. In the bottom, the two pictures are there's some pictures on the left of one experiment, and then the actual setup of the experiment is over there on the right. And you can see me with a couple of our undergraduate students setting up the experiment and getting ready for a flight. And then sometimes you also get to have a little bit of fun on these flights. So mostly it's a lot of hard work, but sometimes you have a little bit of time at the end and you can do a flip or two in microgravity. So this is a short video clip just of us operating that experiment in low gravity on the airplane. You can see us sort of floating around as we come up. We're usually laying down at the beginning because in between the microgravity, you have about 2 Gs, so you have twice as much gravity as usual, so you sort of get pushed down. So it's better, easier on the body usually to just be laying down. And you can see there also that we're sort of doing a bunch of different things and trying to operate the experiment in this clip. And the airplane is actually really crowded. So one of the things, if you ever see photos and pictures of the zero-G flights or some of the other companies, they often are a nice empty plane and people can like do the Superman and fly through them. But usually on the research flights, there's actually a lot of people doing research and it's pretty crowded and there's a lot of really cool experiments going on these flights. And it's disappointing because you don't have time to sort of go around and look at the other people's experiments while you're in the plane because you're working so hard on your own. But those are super awesome experiences to get to have with, for me and for our students. And this is just another picture of some of those experiments from that flight I was just showing. And one of the cool things in this one was we actually had a little accelerometer on it so we could look at what the parabolas look like as we did them. And you can see these sort of here are Martian parabolas, and then we did lunar, and then we went to zero-G. So it's pretty fun. Here's another example of an experiment. So this is an impact experiment. This is like the one I was free floating in that picture a couple slides ago. You can see we bounce a marble into dirt for science. And in this experiment, we were looking at sort of what different types of dirt or regolith in the surface did. And we can see if things bounce off or make a big ejecta plume. And you can see in this case, it was a very sort of stiff reaction and you just get the marble bouncing off instead of that big ejecta cloud. Let's go on. So let's go on then to some suborbital flights. So this is exciting because it's a really new area of research is that we're able to do experiments on suborbital flights. So this means that it's companies right now like Blue Origin and Virgin Galactic that are doing flights with either Spaceship Two, which you can see down in the center, or the Blue Origin capsule that do about 3 to 5 minutes of flight. The way Blue Origin does it is they launch a capsule on a rocket. The rocket separates from the capsule keeps going up until it loses steam and comes back down because again, gravity. But in that time, it's sort of like the top of the parabola on the airplane. And so you're in free fall during that time. And it's about 3 to 5 minutes. And in that time, the capsule does go into space. So there's a lot of different things you can do with these suborbital flights. You can use it to do microgravity science, but you can also use it to study the space environment. So there's a lot of people who are interested in using it to do astronomical observations or study high up in the atmosphere. So there's some really cool chances. Spaceship Two, the Virgin Galactic spaceship, operates a little bit differently, but it also goes up, goes into space and sort of does a bit of a parabola and then glides back down. And these opportunities give us, like I said, a little bit longer in microgravity, so we can do longer lasting experiments or some repeated experiments over the course of the flight. And they're sort of super fun to go out and see a rocket launch or see the plane take off and get to have this opportunity. And as you can see here in these pictures, we have a great opportunity to do these, and often it involves graduate and undergraduate students here at UCF too. So one example of that is this experiment that you can see here. We have a series of experiments called Collide that we've been flying with both Blue Origin and Virgin Galactic. And this is labeled nicely at the bottom as an unsuccessful experiment. So one of the important things about science is that we don't often talk about things that don't work, right? Because that doesn't get you much press. But we do have a lot of things that don't work sometimes, right? And one of the nice things about doing things in the lab or on these suborbital flights even is that we can fix things when they go wrong and then hopefully refly our experiments. So this is a case where sort of the triggering didn't quite go right. So we have to automate all of these payloads because nobody's there to operate them yet. And so the triggering didn't quite happen right. And the marble you can see floating around here launched too early before it was really time for the door to open. So we have some interesting data of this marble bouncing around and can sort of understand how it's behaving in gravity, but we didn't get a good sort of impact experiment that we're used to. But we worked on the project and we fixed a few things, and then we did have a successful experiment. So in this case, you can see on the top, there's a mirror that's reflecting the stuff on the bottom. So you can see that there's a door that slides open, which was supposed to happen the last time. and then it reveals the nice regolith bed underneath. And then we have a marble that launches into the regolith bed and creates a nice ejecta cloud. And so we can use this data to then understand sort of the energies and look at that ejecta and make predictions for planetary surfaces. Also, a lot of these videos come with nice sound effects that you can hear, like the capsule RCS firing and things like that. And I put this little Virgin Galactic picture up in the top right to remind myself to say that we actually have a version of this project flying on the next Spaceship Two flight. So Virgin Galactic has said that the launch window opens on Saturday, the 13th. And so we do have this experiment flying on that flight. So fingers crossed for a good launch and an exciting flight. And then another experiment we've flown on suborbital flights is called Strata. This over here on the right, you can see a picture, sort of a top-down view of the experiment. So to give you a little insight into some of what it looks like, not just this sort of close-up view of the data, but what the experiment actually looks like. So for this experiment, we had some tubes with dirt in them, and we had cameras for imaging and for data collection. And there's a bunch of other sensors in the tubes that we're using to collect data. And then we also have our microgravity indicator. Those have been very popular in some of the flights, the human flights recently, but we've also done it on our flight. And pictured here is Citronaut Dave, who's our sort of mascot. So you'll see him appear in decent pictures, and he has his own Instagram account. But he has gone to space because he was on this Blue Origin flight. I'm very jealous. So here's a picture of him in space. He's actually sort of floating there. You can tell his arms are very jaunty, and he's weightless right now. And you can see over on the right, some of our experiments were activating and moving things around. So finally, we've had ground-based, we've had our drop tower, parabolic flights, suborbital flights, and then finally there's orbital flights. So for a long time, this has meant the International Space Station, which is a great orbiting laboratory where you can do really long-term experiments. So 6 months, a year at a time sometimes. And this gives you a really long-term environment to study microgravity science. And people from all different fields use this. And again, right, biology, life sciences, and it's a really great way to sort of do long-term experiments, but it's hard to get your stuff up there, and you want to test things out really, really well before you get there. So that's why doing things like sort of moving up the chain of what I've been talking about is really important. So you can test your science and your technology before you put it up on the ISS, where it's this really valuable space, and it's hard to fix things if they go wrong. And so we're able to do some really cool experiments on the ISS, and the picture over here on the right is a picture of a computer monitor, but it was of one of our experiments getting installed on the space station about a year ago. And I think one of the cool things about the ISS is that it's actually a really good analog or simulated environment for like asteroids. So the gravity levels on the ISS are really, really low, but they're actually kind of similar to those on some of the asteroids. So it's a really interesting place to study some of these regolith processes I've been talking about. So Strata, I mentioned from the previous slides on the Blue Origin flight, we had a couple of versions now that have flown on the ISS. And so these are experiments, and you can sort of see the tubes better in this picture here. Don't worry about all of the words necessarily, but we have tubes of simulants that we do different types of simulants. We do glass beads, and then we do really high fidelity regolith, simulated regolith, so fake moon dirt, for instance, right? Because it's hard to get the real stuff. But we actually did put a crushed meteorite we hit it with a sledgehammer, broke it up into little bits, and then sent it back up into space to do some science with it. And it did come back. So that was in one of the tubes. And so this experiment flew on the space station for a long time, looking at how these grains move around in this low gravity environment on the ISS. So it's actually a really simple experiment, but having this long-term data was really important. And here's a couple of just time-lapse images. We had still images of the data, but you can see we have these time-lapse images of things just sort of moving around. Oh, and here's another image, which is one of our more recent versions of the same experiment with some different types of simulants. And you can see there's lots of little stuff moving around. And sometimes stuff moves around because of the other experiments around us causing vibration and shaking. Sometimes it's the astronauts walking around that are causing that motion. So it's pretty interesting. So finally, again, in the realm of orbital spacecraft and orbital platforms, are Cubesats. So Cubesats are small spacecraft that can be really quickly developed, are usually lower cost, but they're also usually high risk. And these are being used a lot more these days by commercial companies, but they're also a really great tool for universities and K through 12 schools to build up your own spacecraft. Typically, and I say very, very small, typically these are on the order of between 1 to 3 U, and a U is basically a cube that's 4 inches by 4 inches by 4 inches. So sort of a small Kleenex box. And then a 3U is 3 of those stacked together. So really only about this big. So they're actually very, very small spacecraft, and you have to be pretty clever to figure out how to get everything fit inside of those. And so we've actually built a couple of those, and they've actually both launched now. I haven't been able to say that for very long, but Surfsat was the first spacecraft we built, and I was the lead on that. You can see in the bottom middle there, me holding it very, very gently. I was very nervous when we were taking this picture with some of my students that worked on the project. It was a very large team, so this was just some of the students. But it was a little spacecraft, and you can see on the outside of it, there are different panels. Some of those are solar panels, which give it power. And some of those were materials that we were actually studying how they behaved on orbit. And it launched in September 2018 from Vandenberg Air Force Base on actually the very last Delta II. It was a ride along, so it went with a larger satellite. And then very recently, our second CubeSat called QPACE, which is a really small spacecraft. Again, you can see it in the picture there with Dave for scale and humans for scale. That's studying planet formation. So it's got a bunch of little particles on the inside that are going to be shaken up, and we're going to look at how they clump and how they separate as it orbits the Earth. So they're using that microgravity by just orbiting the Earth to give us really cool science. And that one actually just launched in January on a new platform called Launcher One that's built by Virgin Orbit. So this is a rocket that launches off the underbelly of a plane, which gives it really interesting capabilities of getting to different types of orbits than we've usually been able to get to before. And that rocket is just made for launching small satellites, so CubeSat-sized satellites. And I put at the top, tiny spacecraft, big science. I think that a lot of these satellites have been built for a long time to do some technology demonstrations. There's been some that have been built to study Earth. There's actually been a couple that have gone to Mars now. And there's a lot of interest in using these as secondary science experiments with bigger missions, or as using them sort of to do their own science. And so they're really cool opportunities. They're very challenging. So you think small is going to be really simple, but it's actually really challenging to build them and then communicate with them and all of that stuff. But it's a really awesome opportunity to sort of do a whole life cycle of a whole spacecraft and hold it in your hands. And I think that's my last slide. It was sort of a whirlwind of all of these different platforms. I'll put that slide back up. It's a whirlwind of all of these different platforms, but I wanted to give you a feel for some of these different vehicles that we can use and different ways we can use them for studying all sorts of different aspects. I particularly care about planetary surfaces, and so I use them for microgravity, for low gravity, but a lot of people use them for other reasons and across the science and technology spectrum. So thanks for listening so far, and I am very happy to take questions and elaborate on anything or go completely on a different topic.
All right, yeah, we'll wait for some questions. If you want to type in the dialog box, the Q&A box, you can put it there, or again, you can digitally raise your hand. But I'll start off with a question just to kind of get things going, if you don't mind. Well, first off, I love the Citronaut little person in that picture. So I know it's the old mascot for UCF, and I always think that's a cool throwback.
Yeah, so the Citronaut was the original mascot when UCF was Florida Technological University, and they recently started sort of hyping it up again, and it's the perfect space mascot. So I love it.
I love it. Yeah. So one thing, and apologize if I missed it. Do you ever work with icy particles along with in the regolith? You know, how would that affect some of this science, some of these experiments?
Yeah, that's a great question. I didn't talk about it. We also, for a lot of our experiments, we do dry dirt, dry regolith. And part of that is to really understand how, like the moon is pretty dry, asteroids are pretty dry. So actually like how those surfaces behave, it's really hard to get things as dry as those places, it turns out. But a lot of places like the poles of the moon, icy moons, things like that are icy regolith environments basically. So we do have some experiments that we've been doing with icy collisions or icy columns of material. And there's a few other folks at UCF who are studying that in more detail as well.
Oh, that's great. All right, so we have one question that someone posted here from Christian. He mentions, I know there are a few methods to construct CubeSats. We 3D printed ours. What methods did your team use to build your 2U?
Awesome. Yeah, so there are definitely different ways to do it. Sometimes you can just buy a kit off the shelf. We did design these two spacecraft in tandem. So one ended up being a little bit bigger. You can see on the right, that one's 3U, and the one that I'm holding is 2U. They were designed by students at UCF, undergraduate students at UCF. They're pretty basic aluminum frames. So it's just some aluminum framing. And then the Cubase is just covered in solar panels on the outside, so it can get a lot of power. And then, but we needed fewer solar panels on Surfsat just because we were studying the science of that spacecraft was to study the materials on orbit. So on the outside, it's just a really basic aluminum structure, and then there's a lot more complicated like structure on the inside to support all of the electronics and the radio and the experiments themselves. But it was all sort of custom designed by our students, which is one way to go.
Awesome. Love that. All right. So we have another question from Regan Davis, who asks, where is the furthest planet/asteroid that you've sent a CubeSat to?
So the furthest CubeSats so far have been the Marco CubeSats that went to Mars. So they flew along with Curiosity when, I think that's correct. No, InSight. They flew along with the Mars InSight mission when it went to Mars. And they actually separated a little bit before like InSight landed on the surface. And were actually acted as a technology demonstration. They relayed some data back, which was super cool. And then they did a couple of their own things, and then they sort of just continued and flew by Mars. So they're somewhere, so they're probably farther than that now. There are a couple of missions that are proposed using CubeSats on other asteroid missions. So those might go further out. And there were some small little robots on a couple of other asteroid and comet missions that were little sort of drops to the surface, but those weren't CubeSats technically.
Yeah, it's great seeing where these CubeSats are going, and the use of this technology is awesome.
Yeah.
Love seeing that. All right, so we have a question from Mike who's asking, can you talk about any electrostatic charge experiments and the results?
I feel like I planted that question somehow, but I didn't, I promise. Yeah, so a good portion of my research is I'm trying to understand. So background is the dust on the surfaces, because it's in this place that's basically a vacuum, space is a vacuum. It also interacts with charged particles from space. So this is mostly from what's called the solar wind. So the particles that stream off the sun are electrons and ions, so charged particles. And so that actually can cause charging of dust grains on the surface. So they can be positive or negative relative to each other. And also when they get hit high energy sunlight, they can emit electrons. And so all these complicated processes cause charge on their surfaces. And also, just if you like rub dust together, it will exchange charges, just like if you like rub a balloon on your hair, right? You exchange charges and then it sticks there. That's called triboelectricity. All of these things happen on the moon and asteroids. And can cause motion, can cause dust grain motion just sort of naturally, but it can also happen when you have a spacecraft or a human interacting with those. So I do some of my research is trying to understand what those charges on the grains look like, how they're affected by some of that rubbing. We actually have an experiment that's going to fly on a Blue Origin flight this year that's trying to understand that. So we have a bunch of materials we're going to sort of rub along the surface of regolith and understand how they charge, and then look at the trajectories of those charged particles in microgravity as they move based on what their charges were.
Oh, that's fascinating. No questions continue right now, but maybe there'll be some more in a second. But now that we're a week out from Perseverance being launched to
Yeah.
Mars, what are your thoughts on that? Just kind of general excitement and thoughts on that mission and what you think will happen and what will be discovered, hopefully.
Yeah, so Perseverance is going to be the third to get there, right? Because technically the Mars Hope, the UAE mission, and the Chinese mission have done orbit insertion at Mars, and then Percy gets there next week. I think I don't. I've dabbled in Mars in the past, but all planetary missions, especially surface planetary missions, are exciting to me. And I think Percy will be really exciting because it has a lot of cool technology demonstrations. So demonstrating things like how to capture oxygen from the atmosphere and use that potentially in future missions to like help support making it more habitable and being able to have humans there, for instance. And there's also just some really cool science they're going to do with studying the rocks and shooting. Again, we like to shoot rocks with lasers when we go to Mars. So they're going to do that again. They're going to listen with a microphone to sort of see what that sounds like and also sort of see what the sounds of Mars are. So I think it's going to be, it's similar in some ways to the Curiosity mission, but they've made a bunch of really cool advancements that I think will be really interesting.
Yeah, I think everyone's really excited about that mission, and yeah, we'll see. You know, maybe a past life will be found. Who knows? You know,
Yeah.
it's a big if. You know, but
Yeah.
I think it's very
Yeah.
exciting, and getting
I
people
think,
to think about kind of the work you do, thinking about what's in the surface of planets and how
yeah.
we can learn about all sorts of things.
Yeah.
Not just life. So I think that's
Yeah.
that's great for the science that you do.
Yeah. Yeah. I mean, Mars is also covered in regolith. It's just Mars is a little bit of an atmosphere. So most of the dust there actually is affected by things like wind. And so it's going to be a little bit, and it gets rusty, right? That's sort of why it's that red color. So it will be a little bit different, but it's also covered in dust. So it's super interesting. And actually, one of the recent missions, the Mars InSight mission, had a mole, a little thing that was supposed to drill down under the surface and get pretty deep to study heat in Mars. And they had problems from the beginning because we just didn't really understand what the soil beneath the surface, just a little bit beneath the surface in that location on Mars was like. And so it couldn't dig down the way it needed to. And that was because we didn't really understand how the grains interacted and how that mole would behave in this lower gravity environment. So I've been following that one with good fascination also.
Awesome. Well, I think that's all the questions for now. So I really,
Right.
really appreciate your time on this. I didn't see any more, but you had such a fascinating talk, and the work you do is amazing. It's awesome what you're a part of, and you get to go up in the air too, and all that kind of great stuff. So I love seeing that and love being inspired by people like you and the kind of work that you do, and locally too for us. So that's awesome to see that. So thanks for being part of this, and we really, really appreciate you stopping by to chat about your work and what you do.
Yeah, thanks for having me. I'm hoping to actually fly with some local K through 12 teachers in the next year on a parabolic flight. So hopefully we'll have some cool follow-up that we could show you all for that too.
Very cool. All right. Well, sounds good. Let me just do my outro here. I hope I can get you. Let's see if I can stop your screen here. All right. I appreciate that. I'll come back into the view. Here we go. Okay. Anyway, so thank you guys very much for joining us tonight. And thank you, Dr. Dove, for all that you've done here tonight. Really appreciate it. And we're happy to really celebrate International Day of Women and Girls in Science. And we're going to continue the celebration tomorrow night on Zoom at 6 Eastern, so same time, with a talk by Emily Speck here. Let's get to the right slide there. Emily Speck, who is a space reporter for News 6 and Click Orlando. And she'll be presenting on her reporting on space flight during the commercial space race. You can access that registration for that talk on our website at moas.org. And on Saturday night, at 6 p.m., we are premiering our recorded conversation that our own planetarium coordinator, Jason Schreiner, had with Ariane Cornell, who is the director of astronaut and orbital sales at Blue Origin. Obviously, you mentioned Blue Origin in the talk, so it's kind of a cool connection there. And you can access her talk on Saturday from our MOAS Daytona YouTube and Facebook page. So I'll sign off here. Take care, and I'll say Happy International Day of Women and Girls in Science. And thank you very much, everybody. Appreciate it.